this data, and when you're doing the analysis of it, you need to determine what the uncertainty is in your value, right? Does that make sense? So you got a value, so just remembering, because it's been a couple days since we did this. Ballistic pendulum, so you had the ball bearing, you launched it, it hit that little ring, and then that ring swung up, right? And you found the velocity based on the height that it went, right? Does that make sense? Does that match with what we did? Yes? Okay. And from that, you were able to calculate a velocity that was on the order of like 5 or 6-ish. Does that sound about right? So you have like 6-something meters per second. And that's a lovely thing to be able to say. I know that the velocity of this ball bearing is moving at 6 meters per second. Like, that's cool. But how well do you really know it? That's what I want you to figure out. Okay? That's what this extra part of it was. Because everything that we measure has uncertainty, and I want to know what that uncertainty value was. Okay? So if you haven't done it yet, and we'll do another lab like this in a little bit where you'll have to do this uncertainty thing again. So I just want this to kind of stay in your brain. When you had the expression, it was something like, wasn't it like m1 plus m2 times the square root of 2gh over m1, something like that? Does that look right? So what things did you measure in that expression? We measured m1, and we measured m2, and anything else? The height. So you should be able to tell what your uncertainty, just your reading error, straight up reading error is from each of those things. How do you tell a reading error in a measured mass? Half of the smallest division. So if you look carefully on the triple beam balances, it breaks it down to, I think, the tenth of a gram, correct? So then that means that the reading error, or the uncertainty in M, is how much? 0.05 grams, right? So we could convert that to a certain number of kilograms by moving the decimal over 3 more times. Does that make sense? So that's going to be like something on the order of 5 times 10 to the, I'm doing this right, -5th. Do you guys agree with that? Is that okay? Awesome. What's up, Caleb? Sorry. So that's your reading error in M. So you need to figure out what your percent error is in each of those measured values. How do you do that? How do you find percent error? Right. So your percent uncertainty in M1 is going to be delta M divided by M1, right? And then multiply it by 100. And that'll give you your percent uncertainty. And so then you have a percent uncertainty in M1, a percent uncertainty in the sum of the M's, and then a percent uncertainty in H. And then what do you have to do here? You have to put, how do you deal with those percent uncertainties to find an overall percent uncertainty? Do you remember? This was like day 3 that we were together. It was a while ago. Why don't you open up your notes? Look it up. I know it was there because you did it. I know it was. The rules, yeah. You add what? Always? When you multiply and divide, right? So, do you guys all agree with that? Do you remember that? If you don't remember that, you need to look back at your notes. Absolutely. So you're going to do the percent uncertainty in M1 plus the percent uncertainty in M1 plus M2 plus, is it the percent uncertainty in H? Why 1/2?
Because when you raise it to a power, you multiply by it.
Right, so you're gonna multiply by the exponent. Oops, percent uncertainty in H. Does that make sense? That gives you an overall percent uncertainty. So is that what you write right here where it's plus or minus? I see people staring at me, a few heads moving, I'm not sure.
You have to figure use the 6 again.
Yeah, you have to use the 6 again, right? So percent uncertainty means delta, we'll call it delta V over V, right? So you want to know what delta V is. Does that make sense? You want to know what delta V is, so you need to multiply the percent uncertainty by V. Okay? So it's not super complicated, but it is important to do it this way. It's important to set it up this way so that you've got all of the pieces and so that you have an accurate measure. Okay? Do you have any questions about that? I feel like some of you are looking at each other like, oh, maybe I shouldn't have turned it in yet. Is that true? Yeah? Okay. So let me make a deal with you. I would like to move on and do some other things right now. And then I'll get those out, and if we have some time at the end, we can look at them, and I'll give them back to you for sure. Does that sound okay? Okay. So let me tell you what my plan is for the rest of the day. But I want to make sure, well, before I move on, does that make sense to you, that process? So you know what you need to do. Okay, good. So my other plans for today, I want to do a little physics, like actually do some physics, talk about conservation of energy a little bit more because we get it, but there's more to it. And then I have tests to go over with you also, and to talk about grades and stuff like that. Does that sound okay? Okay. So I'm going to get a new piece of paper. You may want to get a new piece of paper too. And you're not going to let me forget to give you back those things if you want them back. Okay. Okay. New topic. I just didn't want to forget to do that today. So I hope that this isn't too crazy in your brain. Do you remember a couple times ago, I was telling you how much I disliked energy bar charts? Do you remember that? I was kind of going on a rant, I think energy bar charts are stupid. Well, I kind of changed my mind this morning. I'm not saying they're the best thing in the world, but I kind of appreciate them a little bit more today. I don't know. Maybe I just woke up on a different side of the bed or something. I don't really know. But we're going to do them a little more today because I think that it will be good for us. So, here we go. Frog, yes, still. Same frog, same story. I'm going to hold him up here. I'm going to let him know what's going to happen. He's going to fall. It's a wild and crazy ride, right? We didn't even have an idea. What I'd like you to do right now is to draw 3 energy bar charts. 1 when he's up at the top. 1 when he's falling somewhere in the middle. I don't really care where, just, pick something. And then 1 when he gets to the bottom. Before the ground has stopped him, but where he's does that make sense? Before that force is applied, but while he's, yeah. Go ahead and do that. All right. If you were going to teach someone how to draw an energy bar chart, what's one thing you would tell them they need to make sure to do, to keep track of? Yeah?
You have to have the same amount of bars in each graph.
The same amount of bars. What do you mean by that?
To show that it's conserved.
Okay.
Yeah,
So I'm going to have 1 bar here and 1 bar here?
Yeah, and if you add those together, that's the most amount. If you divide, I don't know.
I think you're there. I think we need a couple more words. Keep talking.
It has to have yeah.
He's talking about when you set it up with splitting it up.
Oh, with the boxes.
Yeah.
Is that what you're talking about, David?
Yeah.
Okay. So you need to set it up into boxes, and you need to make sure that you have the same number of boxes in each chart. Does that make sense? Okay. Does it matter how many boxes we choose? No, it's arbitrary. Okay, that's one thing. So we need to make sure the same number of boxes. What else do we need to do to set up an energy bar chart? So if I have this, look at me, I'm so cool. What else do I need to know? What's that?
Label kinetic energy and potential.
Label kinetic and potential energy, right? What kind of potential energy do we have? Gravitational potential, and we have kinetic. Do we have any other kinds of energy in this story? What if we did? What would we do? No, crying is the wrong answer there. At the top, how much gravitational potential energy does it have? What'd you say, V?
At the top?
4 bars. Okay. 100 is a lot.
No, draw 100.
No. I don't want to. You can on yours, but I'm not going to. Okay. Does anybody have other things besides 4 or 100, like apparently Isabel has drawn on her paper? Any other numbers that you've chosen? Number of boxes wise. What'd you have? You had 3. Anybody else? Did anybody have 0? Would that be wrong? Would it?
Yeah,
Well,
you have to, like,
I don't know. It's all based on perspective. Yeah, that's
What, Chris?
It's all based on perspective.
So would it be wrong?
No.
No! Can I do that? Can I put 0, my h equals 0 up here where I'm going to drop my frog from?
Yeah.
Of course I can. So I could start off with 0 energy. 0 total energy. Is that allowed?
Yeah.
Sure. So how much energy would I have here? And how much would I have here? 0. Right? Does this make sense? Yes. Please make sure that you're listening. I feel like we're kind of zoo, and I need you to be here so we can go faster, please. Thank you. What about in the middle? Gravitational potential energy and kinetic energy. What do you know about them now if we use this one as the starting point? They're what?
Are you talking about the middle?
Yeah, kind of in the middle. Yeah.
They're exchanging, sort of.
What does that mean? So use more words, be more specific.
The potential energy is transferring it to kinetic.
Okay, so you've got like maybe 2 boxes of potential and 3 boxes of kinetic. Is that right?
No. We had 2.
You have to.
Yeah, it needs to be-
What's wrong?
You have to keep the same amount of boxes as the first row.
Same and same, right? So I'm going to do 3 there, then I'm going to do just 1 over here, right? Is that wrong? No, it's okay. I didn't tell you where in the middle, but at some place in the middle, the potential energy is going to go down by a factor, right? Like this, that's okay. That's okay. What about at the floor? What about at the floor? What does the floor one look like?
There's to be no potential energy.
Does there have to be no potential energy? Seth, why do you say no?
It's all based, like you said, perspective.
Okay. So I could have my h equals 0 down in Mrs. Cross's room, right? Sure I could. And then if it falls and hits the ground, then does it still have potential energy gravitational? Sure it does. So we have to be careful about saying yes or no, it's wrong. But according to the way that we kind of set it up, it's going to look something like this. And how many boxes are going to be here?
4.
Life is good? Okay. Energy is conserved. Everybody's happy. Okay, now hold on. Here's the situation. I want you to watch carefully. There's the frog. Energy is conserved, right?
Yeah.
Okay. So here there are going to be 5 different places that I want you to look at. So before we even go anywhere, erase your boards. I want you to draw 5 energy bar charts. So you're going to have 5 axes. If you want to do it in 2 levels, that's fine with me. But 5 energy bar charts. Please do not waste my markers. I've had to throw a bunch of markers away already this year, and I have to buy them myself. So don't waste them, because once they're gone, I may not buy more. Okay? So 5 energy bar charts. Once you're ready, put the cap on your marker and put your marker in the air so I know that you're ready. Okay, so here we go. You watching?
Yep.
Okay. This is number 1. You don't have to draw them all. I'm just going to show you all of them and then I'll let you draw. So here's number 1. Here's number 2, number 3, number 4, number 5. So 4 is when it's just getting to the ground, and number 5 is now. Go.
Individually first.
Yep, you can talk to each other, that's fine. But I want you to think about it together.
Where are we going to set it? If we send it underway.
Good progress. Some of you are kind of mad, and I wanna help you so that we're not feeling so. Okay, so let's start by deciding on an h equals 0. Does that sound okay? So that we're all talking about the same thing. Does anybody have a suggestion? Where do you want h to be 0? At the floor. Okay, so I'm going to write that down just so that we don't forget. So h equals 0 at the floor. Okay. Now, talk to me. Talk to me about what you wrote down, what you were struggling with. What were you and your table mates thinking about? You can tell me there are 5 graphs to draw. So tell me about one of them. It's okay to be wrong. It's okay to go out on a limb. Go ahead.
Well, me and Will were discussing and agreed that it has all of its potential energy on the floor and also when you're holding it, because it's not moving, but it has potential energy.
Okay. So what kind of potential energy are you talking about? Gravitational potential energy is defined by what expression? MGH. Okay, so if it's defined by MGH, and you're telling me that the H is equal to 0 at the floor,
No, yeah, you're right.
then what?
Then there would be no energy at the floor.
Jordan, what were you going to say?
I was going to say that, like, if we're only putting, like, kinetic energy and gravitational potential
Mm-hmm.
on these, then we have, like, 1 and 5
Mm-hmm.
empty.
Okay.
Because in 1, it's not moving, so there's no kinetic, and there's no gravitational potential because it's at the floor.
Okay.
But then in 2, it has obviously potential energy because it's off of the floor.
Okay.
And so, like, these graphs don't show, like, all of the energy in the entire system. So, like, you were exerting energy to move it, like, up. Like, in the motion from it being in the floor and you lifting it up, you were exerting energy on it, so the energy was conserved to give it that gravitational potential. So, like, for conservation of energy to work, then it has to show the energy of, like, everything in the system, like, including you and the floor, kind of.
What do you guys think of that? Does that seem to kind of make sense, to jive with you? Yeah. So the whole point of this is exactly right. The whole point of this is to figure out what we're considering a system. And that's a really, really big question. What is in the system? In the first example that we did, what were we considering the system to be? What was in the system? The frog. The frog, yeah. Is it okay for the frog to be the only thing in the system? Sure, you can pick anything. The cool thing about this energy stuff is you get to pick everything, right? You get to pick where H equals 0. You get to pick what's in the system. Like, you are in control, right? This is a big deal. But, as Jordan said, so I'm going to put something in between these two graphs. I'm going to put a circle in here, okay? And that circle represents the system. If I have no energy going on here, and I have some here, is energy conserved in this story right here as I have pictured? Does 0 equal 4? No, so is energy conserved? Come on, friends. Say it out loud.
No.
No! Believe it! Is energy conserved?
No.
It's Friday afternoon. You're not that tired. I'm going to ask it one more time. Humor me. Is energy conserved?
Yeah.
No! The answer is no, it's not. River, wake up, my buddy. We need to get this figured out. Jeez. I'm trying to teach, all right? Jeez. River wants you to know. Yeah, they just come to see me after they see you. They were all mad. Was that what you guys were mad about? Were you mad at Marchetti? Oh! I'm going to pause this for our friends that aren't here. Sorry. Energy is not conserved. We just said that again. So this is all kinetic. So we've got, what, 4 bars of kinetic or something like that? And then we're going to have this little circle thing here. Again, that's the frog. And what's happening this time? Yeah, there's energy that's leaving the system. Where's that energy going? Into the floor. It's true. Does that kind of make sense? Is that okay? So what we just proved here is that energy is not conserved. Well, that's a frustrating situation because all of physics and all of the universe is based on the theory that energy is conserved. Dang it, so we just broke physics. Guess we're done. Except we're not, because Jordan did save us earlier by saying that we can just define our system bigger, right? So in what system is energy actually conserved? What do we have to include in our system? Me and what else? And the frog and the floor, right? So let's do that just for kicks. Here we go. So we're going to do the same story. So you can erase your bar charts, but maybe leave the axes, except he's like, wait, I just started erasing. Well, you can add those axes back in. I want you to draw bar charts if the system includes me and the frog and the floor / air, I'm going to say. 5 bar charts again. 5 bar charts again. I want to know what they're going to include. Maybe you're going to have more than just 2 things on your x-axis now. Do you think? Talk to your partners. See if you can come up with an idea. What are you going to do to make this a more complete story? Toast. Peanut butter toast energy. Yeah. Yeah. So when it's on the floor, we have all kinds of energy. We have gravitational potential, as we know. We have kinetic, and then you added some other ones with all kinds of awesome names. But if we're going to be official about it, it's a type of potential energy, right? It's peanut butter toast potential energy. If we were going to be a little more formal than that, we'd probably call that what kind of energy? What kind of potential energy?
Yeah,
Chemical potential energy, yes. That's chemical potential energy, okay? You consume things, your body converts that stuff into the energy that allows you to do stuff. And so that's going to be where all of our energy lives at the beginning. And then we know what these guys look like, right? The held high and the da-da-da-da-da. So I convert 4 boxes of chemical potential energy into the gravitational potential energy that is what the frog has. Does that make sense? And then the frog falls, as he always does. And then what happens right here between the floor and when it stops? What happens?
I think the energy is transferred into the floor. I'm not really sure what type of energy it is, but like because it's like forcing it, like giving it energy.
Yeah, it's giving it off, right? So it has kinetic energy. It hits the ground. And if you think about it, it's all kind of squishing around and moving around and stuff like that. And that is causing something to be given off. Some of it's sound. A lot of it is actually kind of the same thing as friction. It's heat energy, thermal energy. Yeah. Yeah, it's thermal energy that's coming out. So I would also include some sort of, we'll call it heat here. And there's no heat there, but I would put all of that 4 bars of energy in there. Now, there's a lab that I do with, that I will do with the AP Physics 2 people next year when we do thermo. But actually, hold on. Let me go get it and I'll show you it because it's kind of cool. That's all exciting. But it's got shot in it, okay, little BBs in it, okay? And I put a little hole in one of the ends, and the lab involves this. Over and over and over like 100 times.
Sounds
Okay? Very exciting. It's actually lovely. It's kind of, you know, it's kind of like Zen after a while. It's like, ah. Right? So what's happening here? Chemical energy, right? My peanut butter toast is turning into gravitational potential, kinetic, and sound and thermal energy. And what we do with it is that we take the temperature of the ball bearings before, and we take the temperature of the ball bearings after. And you can tell how much energy they have, right, because I'm lifting them up gravitational. So I can calculate how much gravitational potential energy there is. And then that gravitational potential energy turns into kinetic. And that kinetic turns into thermal. And it's actually a measurable difference in temperature from the beginning to the end. What's that?
Even if it's the first time around, you can tell.
Well, that's why we have to do it 100 times, right? Because if you do it just once, and you have to have a really good thermometer, right? With a very, very small, or lots of symmetric figures, if you will. But if you do it a bunch of times, then yeah, I mean, it goes up by a few degrees, which is kind of surprising, isn't it? But that's what's going on. Okay, life is okay here? Does this make sense to everybody? Okay, so the game is, just like we said with setting h equal to 0, you can set your system to be whatever you want it to be. Sometimes it's more convenient to talk about all of these things like the floor and the person and whatever. Sometimes it's less convenient to talk about that. You want the system to just be one thing. And if you want the system to just be one thing, then you have to acknowledge that sometimes energy is added or removed from the system. There is one system from which no energy can be added or removed. That system would be the universe, right? You can't get any bigger than the universe. Because even if we're just talking about the frog and me and the floor, well, then there's the air, right? And the air is impacting the outside. Like it's a ripple effect out and out and out. But if you talk about the energy of the universe, it has to be the same all the time forever. Okay? From the Big Bang to now, same amount of energy. Not same amount of order and disorder, but same amount of energy. Okay? How do we change the amount of energy in this story? Just to kind of regroup and get this around in our heads. I was able, so Karbeling added energy to the frog, to the system. If we call the system just the frog. What kind of energy did I add? Potential, gravitational potential, right? How did I do that? What did I do?
You lifted it.
I lifted it. Let's be a little bit more specific. What did I do? Let's talk about it in physics terms.
You grabbed it.
I grabbed it and I what? I changed the height. How did I do that?
Apply force.
I had to, I do, like it was sitting there, right? It was sitting there. It's just hanging out. In order for me to get it from there to there, I have to definitely displace it. And in order to do that, what do I need to do to it? I need to apply a force. Okay? I have to apply a force to get it up here. Does that make sense? So I had to apply a force. It is. Okay? A force had to be applied over a distance. That is called, what was it? Work. So work, which is marked with a W, is equal to the change in energy of a system. So by doing work, I'm changing the amount of energy in the system. Okay? I'm applying a force over a distance. Let's talk about another situation. If the system is just the frog, what else changed the amount of energy of the system? What else changed the amount of energy of the system? Let's look back at the picture. What else changed the amount of energy of the system? The floor. Right? How did the floor do that? What did it do?
It's the frog.
Let's talk about it in terms of physics. What did it do?
Applied a floor.
It applied a force. Don't you agree? If the floor wasn't there, the frog would just keep falling. But the frog applied a force. Yes? I'm going to say over a distance. Does that make any sense? Watch the frog fall. He lands like this, and then what happens? So there's a little bit of a distance that's happening there, right? Okay? So the floor is, what do I want to say? Decreasing the energy of the system. And the system, again, here is the frog. So the key here, friends, is that you have to make sure that you define the system. Okay? In this case, the work was changing the kinetic energy. Okay? The work changes the amount of energy in the system by applying a force over a distance. We doing okay? Is this making sense? Okay. I want to think about it in terms of a couple of problems here. Oops. I think I want to do this one first. Let's see. I don't know if you can read this very well because it's kind of a funny picture, but let me make it a little bit bigger and then I'll read it to you so you can certainly understand what's going on. So it says the velocity of a tugboat, so tugboats instead of frogs, but same kind of deal. It increases from 2 meters per second to 4 meters per second in the same direction while a force is applied to the tugboat for 20 seconds. Does that make sense? So we can look at this, friends. This is like a kind of a weird thing. If you have a force applied for a certain amount of time, it's also changing the what of the system? Say it loud.
Momentum.
Momentum! Yeah, it's changing the momentum too. So this is weird. We're changing the momentum. We're changing the energy at the same time. Oh, they're like related. Whoa. All right. This thing says complete the work energy bar chart. So they're throwing work into it now because the system is just what? What's in the system? Just the tugboat. So the tugboat is the only thing in the system. Okay? This one wants the bar heights to be proportional so that this matches. I want you to talk to your neighbors about how you might do this and go ahead and write it on your boards. Okay? Let me make this a little bit bigger. Have a conversation. See if you can figure. Can I pose a question to you? May I pose a question to you? Is the kinetic energy going to double? Jordan's adamant. She gets cranky today, we know, so let's watch out. Yeah, why do you say no? I mean that in the nicest possible way. Uh-huh.
And we know what V is for that. So we figured out what the mass was, and it just does a mass of 1. But then your kinetic energy has to be equal to, for the final one, has to be equal to 1/2 of the velocity squared. And since the velocity is 4, then the kinetic energy has to be equal to 8.
Does that make sense? People at her table are like, yeah. Sure. What are the other tables you guys think? Chris, what do you think?
That makes sense.
Yeah? Will, what do you think?
I think that makes sense.
But I guess so.
Okay. Well, let's make sure it makes sense for real. Does this statement make sense to you all? There are 2 bars, and that equals 1/2 m times 2 squared. I want to know how many bars are equal to 1/2 m times 4 squared. This is, oops, let me do this in the right color. So this is 1/2 m times 4. Does that make sense? This one is 1/2 m times what? 16, which is really like 1/2 m times 4 times what? 4, is that okay?
Yeah.
So this one needs to be how many times higher than this one? 4 times higher. 4 times 2 is 8. So there you go. We need 8. We need 8 bars. So that's 1, 2, 3, 4, 5, 6, 7. I think that's 8 there. Which means what needs to go? 2, 3, 4, 5, 6, 7. Okay, did 8. How much work is done then? 6 bars. 1, 2, 3, 4, 5, 6. Is that okay? Okay. I'm going to put one more up there. There's actually a part B to this question. I want you to work on part B by yourself first. I'll give you a minute or so to think about it, and then I'll let you talk. But I want you to try it out first by yourself. Here it comes. It's a similar looking question. It says the velocity of a tugboat changes from 2 meters per second to 4 meters per second in the opposite direction while a force is applied to a tugboat for 20 seconds. Complete the work and energy bar chart for this process. The bar heights should be correct in proportion to one another. So I'm going to let you chew on that by yourself for a moment, and then we'll discuss it. Figure it out. Help me out. So there are some people that have similar things to last time. Some people have more things. Talk me through your reasoning. Someone, not Jordan, she's talked too much today. Somebody else talk to me. I don't care who it is. David, back there, talk to me.
Alright, well, so the
Or you can call on somebody else.
yeah, I'm not exactly sure what I'm doing here. But what I initially thought was like, I don't know.
You can pass if you want. I don't mean that in a. I just.
Oh, yeah, okay.
I was just wanting to say, like, it can't be the same as the last one, even though, like, even if you, like, put -4 as the velocity and then square it, because it require more work to go the opposite direction. So that's why I thought it'd be, like, the distance from -2 to 4, so I changed it to 6 as, like,
Okay. It can't be the same because it's going the other direction. That's what you said, right? Others, do you agree? So what did you have? You had how many here?
For which one? What do you want?
For the kinetic energy, how much did you have?
18.
18. And then you had, so 16 there?
Yeah, but it seems a little high. I don't know.
So was it kind of arbitrary, or was it like a reason, like did you make that decision on purpose? Of 18.
You use the equation.
Yeah, I used, like, the equation, but substituted in that velocity was 6, because you'd have to overcome the 2 going to the right, and then the 4. I don't know.
Okay.
Yeah.
Okay. Other people?
Makes
Chris?
You said that it was the same as the other one,
Why?
since if you substitute -4 into the 1/2 mv squared, it just equals 16 again because of the square.
Okay.
So it wouldn't change, it would just be the same as the other one.
Okay.
Direction.
Other thoughts? So 1 vote for the same, 1 vote for different. 18 because it can't be the same. So it just doesn't make sense for it to be the same, right? Because we've been so darn programmed that if we're going one direction, we turn around and go the other direction. That by golly, it must be different, right? But energy is or is not a vector. is not a vector. It's a scalar. We just want to know how much. So here, the force that's causing this to turn or to go this way is just pushing in that direction, right? And remember that this isn't that we're not just marking the force. It's going to take a different force. I would agree. But all we're talking about is a change in energy. Work is just a change in energy. So we look at the energy before, we look at the energy after. The energy before is 2 blocks, which equals 1/2 m times 2 squared, right? The energy after is 1/2 m times 4 squared. So it should be how many blocks? Justin's excited because it should be how many blocks? It should be 8 blocks. Yes. Yeah.
Okay, I had a question. When
Yeah.
we were talking about like, the definition of work, though, we said that it was a force applied over a distance.
Yes. I agree.
So,
We have nothing in here that says anything about distance.
That's what I was like.
Work also equals the change in energy.
What's that?
Work also equals the change in energy.
Work is the change in energy. It is a force applied over a distance, right? So it's not instantaneous. So the force here is going in which direction? This way, right? This is the negative direction or something. Yeah, it's going this way. That's all well and good. We don't know how far it goes. All we know is a snapshot here, it's going 2 meters per second. A snapshot here, it's going 4 back this way.
but, like, if the forces are different between the first one and the second one, then how is their work? Does that just mean that their distance?
Because the distances would be different too. Yeah,
Okay.
yeah.
So the distances will somehow make it so.
I mean, we could do the math. I mean, let's talk about how we could do the math. Let's not do it just because I'm looking at the clock. Is that okay? If we could figure out if we have an initial velocity of 2 and a final velocity of 4 and a time of 20 seconds, we could figure out how far it goes, right? And you could do it for the other one too. And I'm guessing the distances wouldn't be the same.
Yeah, so the distances and the forces would somehow like make it so that it's
Right, so a big force over a little distance or a little force over a big distance.
okay.
Yes. Is that okay? It's a good question. It's not intuitive, especially because we programmed ourselves to really care about directions, right? Directions don't matter anymore. That's a little bit weird in this stuff. Okay.